And welcome for part 2 of the uh, derivative of e to the x video. This is all about explaining, or trying to anyway, why this limit is true. And we said probably our instincts would be, let's just try some values of h that are close to 0 and see if indeed that it goes to 1. And when we first started evaluating limits, this is what we did, and so maybe this would make sense to do here. This is what I'm going to do first. This is going to be my first effort, is a numeric effort, but I want to show you a trick too. Well, not a trick. I want to show you how to use some technology to do this. Notice what I've put in is I've put in this function. Notice that it's not an h, but it's an x. It kind of means the same thing. And I'm not interested in the entire graph. I'm just interested in this graph near 0. And so I'm going to actually use the graphing calculator to come up with the table of values for me so I can fill this in and think about it. And the way I do that is I press second function table, but notice it's got all these values, including 0, which is what I'm interested in, and it gives me an error. Well, that makes sense. That's because it's 0 over 0, which is indeterminate, which is why we're having the trouble in the first place. But what I can do is I can set up my table, and it will ask me what x values I'd like. And this is going to be cool because I can put in whatever I want. So for instance, if I wanted it to be close to 0 and closer to 0 and closer to 0, I can do that very quickly. It's much, much quicker than you pounding some values into your scientific calculator. And notice that every limit, has two sides, a left side and a right side that we should be thinking about. So let's go from the left side as well. And I'll put these values in here. Oops. 0, 1. And notice, yeah, it's getting close. It's getting closer to 1, just like we expected. Okay, I'm going to put these values on my table and then report back. Hey, bam, there it is. So there was the values for getting close to 0 from the right and getting closer to 0 from the left. And notice when we first talked about limits existing, we did talk about that the left-hand limit, or the right-hand limit and the left-hand limit, have to be equal. And we did a table to calculate that. We did a table to calculate that. So it appears that this limit is equal to 1. Now, we accepted that value as fact anyway, but you know, we could be happy at that numerical method. But not very satisfying. It feels very kind of wishy-washy. Maybe something weird happens that we wouldn't expect when it got closer and closer to 0. Maybe we should try and use a more rigorous approach, a more calculus-y approach. And rigorous isn't another word for difficult. Rigorous is a math word for airtight, logical, arguable, that sort of thing. So I'm going to start with this argument from this definition. This definition of E. We saw this the other day. This was the bank interest, right? Where we got 100% interest every n quarters, but then there was n quarters, or n periods in the year, and as n went to infinity, this went to E. And in fact, we kind of defined E to be this way. And what I'm going to do is essentially I'm going to turn this fact into that fact. All right? So first of all, think of this 1 over n as h. Notice then, as n goes to infinity, what does h go to? Think in your head. Yeah, 0. Goes to 0. So this limit changes. Then E is equal to the limit as h goes to 0 of 1 plus h, and then n, when all I have to do is flip both sides. This is 1 over h then, right? Well, I'm going to do something strange. I'm going to have both sides to the raise both sides to the power of h. Okay? Not square it. H power. H, that's hard to say. H power. h power. But if you remember from our limit rules, when we have an exponent on the inside, it also acts on the, or so exponent on the outside, I can suck it into the limit on the inside as well. So this actually becomes, because of our limit rules from way back in chapter 1, unit 1, becomes 1 plus h, this inside thing here, all to the exponent h. This is a limit rule. No trixies yet. This is all good math so far. But then I got 1 over h to the exponent h. Those exponents cancel. You see that? Now, notice if I'm thinking about h going to 0, then I have two limits on this side. And now think about this. Then, if I build this limit as h tends to 0 of e to the h, you can kind of almost think of taking the limit as h tends to 0 of both of these sides. Okay? And think of it that way. Then e to the h minus 1. This is what we're interested in. Well, what's this thing equal to? That thing's equal to this thing. E to the h is equal to 1 plus h. These two things are the same. Equals the limit as h tends to 0 of 1 plus h minus 1 over h. Well, that's the limit as h tends to 0 of h over h. Those cancel, which is 1. And even the rigorous face is happy. Now, as it turns out, neither of these are the real reason why this limit is true. Although they both explain it just fine. Here's the third and maybe kind of strangest reason. E is defined as the value of b, a base b, not a 6 there, that's a b, so that the limit as h tends to 0 of b to the h. So this is mathematicians a long time ago. They were thinking of, all right, if I have an exponential function of some sort, let me just get it. And we're interested in having some exponential function so that the slope of this tangent here, which is just the change in y over the change in x, is equal to 1. Well, we want to know what value of b this would be true. Well, what's the slope of the tangent? Well, if I went from here, this is the point 0, 1, and this point on the graph here is just, well, let's say it's h e to the h, right? And we're interested in, this is the change in x, which is just h minus 0. And then this little distance here is the change in y, which is, what was that, is e to the h minus 1. So we're interested in finding out what base makes this 1. And they said, okay, well, we're not sure if there is such a number. 2 didn't work and 3 didn't work. We're going to call the number that does work, we're going to call that e. And in fact, all of this limit business all comes to the definition. E is defined by this limit because of this picture. They needed to find the function where this was true, where this slope of the tangent was 1, and in fact that's where e came from. And all of this other business led after this, after the limit, after the limit existed. So there's a short story long. And again, what do you need to know? You need to know this is true. If you remember one of the reasons why, that's even better. Okay, on to the homework.